Hello, hello. Yeah, this works. Good afternoon. I think it's time to start, so I see no one around here giving me the word, so I give myself the word. So my name is Jan Venderly, and I'm the Director of Nuclear Export Technologies at EDF in the Division of New Nuclear Development. And I'm really very pleased to have this opportunity today to present you EDF's strategy, international strategy in the development of new nuclear reactors around the world. And specifically more focus on the reactor portfolio we propose for that. I hope can you hear me clearly? Is that okay? Yeah, thanks. Before getting into this, I'd like to say briefly a few things about our company. If this works, yes, it works. As you probably know, EDF is a global, fully integrated energy company and operating and developing all over the world. We cover virtually all sectors, from generation to trading to transportation, distribution of energy, and of very low carbon electricity. So our priority is not only to provide safe, reliable, and affordable energy to our customers, but also to contribute to a sustainable society, specifically a low carbon future for the next generations. And it is really our duty to help limiting climate change as much as it's in our ability. You probably know that EDF is one of the biggest nuclear operators, utilities worldwide. Wow. But perhaps you do not know that EDF is also Europe's #1 renewable energy producer. And I thought it would be nice to show you this picture, which is the European carbon intensity on a typical day, let's say, somewhere in September. And you see that France is green in this area. That's because our electricity is for 97% free of direct CO2 emissions. So France is green every day, every week, every month of the year, which is nice. And that's because we have of our nuclear park fleet, 70% is nuclear, and the remaining part is mainly hydro and a little bit of intermittent renewables. So our main nuclear assets are 56 nuclear power plants in France, in 18 different sites, and 13 nuclear power plants in the UK. And a couple of other figures are given here. 50,000 people are working in EDF's nuclear business out of roughly 160,000 people in total. But I thought, and I think that what of most interest for you is to have some information about our reactor portfolio, which is shown here. So our long-term international strategy is based on 3 different projects or products, and these are all pressurized water reactors, PWRs. Firstly, we have the EPR, our flagship, a 1650 megawatt generation 3+ reactor. Secondly, also part of the EPR family, it's the EPR 1200, which as implies by its name produces 1200 megawatts electrical output. And thirdly, and it's our newcomer, still in development stage, Newor, the small modular reactor, which embarks 2 fully integrated PWRs of 170 megawatt each. Now, about the EPR technology, I would like to start a little bit about the EPR technology, which is really at the basis of our export strategy. It is the world's largest nuclear power plant, commercially available. It is a significant evolution with regard to the generation 2 reactors EDF has built and operates for more than 50 years now. It has a lot of additional safety systems. I'll come back to that. It has a well-proven 4-loop primary coolant system with an output of 4,600 almost thermal megawatts. Most of the safety grade systems they are built in or designed with a four-fold redundancy, and they are located in these 4 different divisions you see here in colors, which are physically separated from each other for safety reasons. So it's fully compliant with the latest international recommendations, including the ones from the IAEA, from the Western European Nuclear Regulators Association, WNRA, and the European Utility Requirements. And of course, the EPR integrates and takes into account all the post-Fukushima lessons learned as well. In terms of performance, it is one of the features I personally really like about the EPR. It's really its core. It's a pretty big core, 241 assemblies, which allows you, combined with a dedicated heavy neutron reflector, to consume about 20% less of uranium. That's nice. Even nicer, it allows you for a more optimized fuel management, a little bit more flexibility, and a more smoother operation of the plant, which is highly appreciated by the operators. It allows also to burn MOX. So I think that's an interesting feature. The other one is that you have these 4 steam generators, which are well-proven U-tube heat exchangers, but they're equipped with an actual flow economizer, which allows you to, there's a specific design which allows you to improve the heat exchange between the primary and the secondary side of the system, and to increase the pressure. So you have an increased pressure compared to standard steam generators, which have the same surface area for heat exchange. So that allows you, combined with a pretty efficient turbine, to get to a thermal efficiency of 37, even 38%. So it's a highly efficient nuclear reactor. Another worthwhile to mention point is that per kilowatt hour produced, operation and maintenance costs are reduced because you can operate, mainly because you can operate a big plant like this with the same amount of staff as you use for a mid-size reactor. But also because of what I said just before, a more flexible fuel management of the reactor. And a couple of other parameters, operating and performance parameters, are listed here. And for the sake of time, I will not go through all of these here. I would like to say a few words about the safety design. The EPR safety design is based on the well-recognized defense in depth principle, which follows the IAEA's recommendations and standards in terms of safety. So that means a very, very low probability of severe accidents with core meltdown, minimized impact on the population in case there would be such an accident, and a reinforced resistance to external hazards. And that includes earthquakes, airplane crashes, explosions, extreme weather, droughts, tornadoes, you name it. So compared to Generation 2 PWRs, the EPR has quite some improvements in all the 5 levels of defense in depth. So I think the most important point I would like to make here is that because if you increase the prevention and detection levels, if you increase the performance in these areas, you actually will avoid reactor trips, because you give the operator more time to react, for example. And that allows you to, of course, to increase the availability of your plant, to limit the loss of electricity to the grid, but also to reduce the number of loads and transients, which is good for your plant management and aging management. So you keep your plant in a healthier stage for longer periods. So I think that's an important point we could make here. Another spectacular safety feature is the core catcher. So that's the part of the EPR's mitigation and severe accident management. So would there be a core melt accident, the first demelt would be temporarily retained within the reactor cavity, and that's because we want to be sure that we capture the full reactor core inventory. And then a core plug melts, and that's a passive process, And the core melt spreads out over the core catcher area, and then will be flooded with borated water. And what you see here in the picture is an experiment which was carried out by the CEA. And you see that was to study the flow behavior of this very, very hot melt, and look how your sacrificial concrete would behave in these conditions. So, so I mentioned here a passive process. I thought it was also perhaps interesting for you to see how the EPR deals with passive and active processes. So, nuclear plant designers all over the world, they are addressing the potential use of passive systems in order to simplify the design, to reduce costs, but also to increase the safety standards. And of course, EDF and the EPR does not make any exception to that. So we're looking into these features. So EPR's safety design is based on these active systems and completed where and when it makes sense with passive systems. For example, one example is the passively activated accumulators, and a couple of others are listed on the screen here if you can read it. The advantage of this mixed approach between passive and active systems is that active systems, you can test them periodically. Sorry. You can inspect them easier. They're sometimes easier to build. It's easier to put in a pump, for example, than to build a convective cooling system, for example. So they do not need to be manual. Active systems can be totally automated, which is exactly what we do, of course. So by using both systems and completing them, we think that the EPR is the safest PWR design out there today. And well, this was nicely illustrated before in the previous session, but a nice feature of the EPR and the EPR family and EPR 1200, as I will illustrate later, is the load following. So those who were present in the previous session, you had the nitty-gritty of it, but the EPR can fairly quickly ramp up and follow the load up to twice per day from 25% to 100% in 30 minutes. So you can really follow, as you see in the graphs here, this is from the current fleet. You can really follow the load, especially in when you have more and more intermittent energy coming to the grid. So that's a nice feature, which is really part of the EPR design and one of the unique know-hows of EDF in this domain. Okay, so internationally, we are currently well, 2 EPRs are running in Taishan. We have 1 EPR, as you all know, under commissioning stage almost in Flamanville. So the fuel will be loaded by the end of this year. 2 EPRs being under construction in the UK at Hinkley Point C. Projects are under development for Sizewell in the UK as well. We have an exciting project going on with India in Jaitapur. 6 EPRs. That will be the biggest nuclear power plant of the world if that project could be built. And we're looking forward to it to make this happen. And other projects in Europe. So, for example, the Czech Republic, Poland, and other countries. So there's quite some areas in the world where EDF is working on developing of nuclear power plants. So stay tuned, because it goes very, very fast. Let me say a few words about the EPR 1200. So the EPR 1200 is typically a power plant for countries who want to address decarbonization of their energy mix, but where the EPR, because of its high power, is not suitable for whatever reasons. For example, for the Czech Republic, they want to build another power plant at the Dukovany site. We cannot put an EPR there because their grid capacity doesn't allow for that, so we propose the EPR 1200. And there could be other reasons to go for a mid-size reactor. So what is the EPR 1200 in a nutshell? EPR 1200 is an EPR. It is fully built on what we call the CoreEPR technology. Now, what is the CoreEPR technology? It is that invariable set of technical choices covering safety and non-safety design of systems and components, as well as codes and standards, which are used by all EPRs. This set of choices, they are resulting from the experience we have with the new build projects and optimizations we have found and which we apply. So most safety-related components of the EPR 1200 are standard. For example, steam generators are the same as the one we use for the EPR. Primary pumps, the core catcher, systems, and many more. Well, the different components here in this case are, of course, the reactor pressure vessel, which is slightly smaller, and the number of fuel assemblies, because we want to reduce the power to 3,300 thermal megawatts, 1,200 megawatts of electrical output. So this very strong affiliation with the EPR itself, we believe is a success factor for the EPR 1200, because first, there's not much redesign required, because we use the CoreEPR technology. Second, we can build upon the licensing experience we have with the EPR in different countries, 4 countries, and 3 of them are in Europe. And third, there is an opportunity for a lot of synergy if we have these different EPRs being built concurrently for example, in Europe. So that would be, for us, a major advantage of using such an EPR family. Now, last but not least, because I've seen that's a popular topic today, is Newor, which is the EDF's integrated small modular reactor. So that's typically one of the solutions we propose internationally for countries looking to replace coal plants, for example, or to remote areas, industrial areas. And it's also pretty complementary to bigger nuclear energy if that's required. So, the Newor is it's also as I said before, it's a pressurized water reactor. It's actually 2 pressurized water reactor in one plant. Each of the reactor has 540 thermal megawatts. That's 170 megawatt of electrical output, roughly. So if you have one plant, it's 340 megawatt of electrical output. It has a fully integrated pressurizer, steam generator, and these are very innovative. They're very compact steam generators. It has a pretty standard core. We just use the fuel we always use, but a smaller, of course, number of assemblies, 76 assemblies. The reactor is built, located in a metallic containment of about 16 meters high, which is fully immersed in water. And the entire structure, as you see on the picture, is partly underground, which helps in protection against external hazards. So with regard to the performance of the Newor, we want to offer, of course, a reactor with the same performance as we can offer for large EPRs. So it has the same level of ability, the same lifetime of over 60 years, etc. So Newor is still in development stage. So we expect to enter the basic design phase and the pre-licensing of the Newor by the end of 2022. So that's in 1 year. By 2025, we expect to be able to start commercializing Newor, and we are looking forward to start building the first reactor here in France by 2030. So in a nutshell, that's about Newor. There is a specific corner at the EDF stand where you can learn much more about Newor. The director of the project is there to explain you more about this specific plant, as well as the commercial director if you are interested in Newor for your country. So in conclusion, I'd like to emphasize a few points here. So nuclear, as you have seen here, and as you heard this morning, is and remains the principal energy generation asset in France. And EDF is in full speed to prepare the next generation of nuclear. Our reactor portfolio is composed of 3 pressurized water reactors. 2 of them are part of the EPR family, and we have Newor, the small modular reactor. And they allow, according to us, to respond to all major market needs for the next decades to come. So EDF is strongly involved in and committed to new build activities all around the world, including in the UK, including in close by countries far away, and we are at your availability to discuss if you're interested in one of these projects specifically. And we're building with these products, we believe, a low carbon future for the next generations to come. So I thank you very much and wish you a wonderful WNE this afternoon and the rest of this week. Thank you very much. So if there's any question I could answer here, it's fine. And otherwise, I think there is a booth specifically dressed up for